Lab 3, Black Hole in Orbits. So to introduce this lab, in the first part, we created a glow script model to calculate the mass in black hole using Newton's second law and the gravitational force between the star and the black hole. In the second part of the lab, we simulated the motion of the spaceship attempting to achieve a figure-eight motion around a planet and its moon by calculating the gravitational interactions among all three bodies. Now, when looking at fundamentals, the main fundamentals for this lab is Newton's second law and the momentum principle, where Newton's second law states that force equals mass times acceleration, and the momentum principle describes how force relates to an object's momentum. The parallel component then shows the net force determined by an object's speed, and the perpendicular component is the net force that affects the object's direction. Some other fundamentals is the gravitational force used by the universal law of gravitation, where the gravitational constant is 6.67 times 10 to the negative 11th. For the first part of our computational model, we look at the initial conditions, which provide the position and velocity of the star, the gravitational force between the black hole and the star, and the time step adjustments to simulate the motion accurately. The main code of the computational model in part one included observations that the orbit was elliptical and that the gravitational force was weaker when the star was farthest from the black hole, which is affirmed by the equation that states that when the radius is bigger, the gravitational force is smaller. Now, the potential source of errors that can be found in this code is that rounding the gravitational constants at each value could lead to improper calculations, and that computational approximations affect precision. The final values that are found in this part were that the net force is 9.840 times 10 to the 28th, the parallel component is 2.715 times 10 to the 28th, and the perpendicular component is 9.434 times 10 to the 28th. And the estimated mass of the black hole was 1.707 times 10 to the 34. Now, when we look at the initial conditions of part two, we move into a spaceship attempting a figure-eight orbit around a planet and its moon. When we look at the results of part two, it shows that the closest distance between the spaceship and the black hole was 1.0754 meters, and that the maximum gravitational force was experienced at the smallest distance, which is affirmed by the equation. Some other potential sources of error was rounding and then small numerical accuracies. So, when we look at what if, we can interpret that mathematically the net force and the rate of change of momentum are the same. However, calculating net force requires knowing that black hole's mass, whereas momentum change can be determined only using time, position, and velocity. And that the parallel and perpendicular components of force correspond to the rate of change of momentum in different directions. And now, when we ask the question, what if you wanted to enter orbit around the black hole? What initial velocity would your spaceship need? We can answer it by saying specifically the x component of the velocity would need to be known, and it would need to be in a smaller magnitude in order for the to have a stable orbit instead of escaping trajectory. And to conclude, the lab allowed us to use gravitational forces and orbital motion to using computational methods, and we successfully estimated the mass of the black hole, modeled a complex orbital path of this black hole, and then experiment highlighted interplay between force, momentum, and trajectory, as well as the effects of rounding error in computation simulations.